this point, we're going to move on to our next panel, the Advanced Materials in Space, Expanding Fundamental Knowledge and Progress in Orbit Manufacturing panel. Brings together government and industry experts to discuss the early successes and challenges of in-orbit manufacturing and the dramatic impact such capabilities would have on scientific advancements and commercial operations both in space and on Earth. Our moderator will be Dr. Ken Savine, who is the Director of Commercial Innovation and Science and Technology team at the ISS National Lab. I'm not going to go through Ken's complete bio in the interest of time, but suffice it to say he started off at Eli Lilly as an organic chemist, and he moved up through multiple positions of higher responsibility over the course of about a decade or more. He was very upwardly mobile. And so please help me welcome Ken to the stage now.
My responsibility here is to try to get you engaged in material science, to think about material science on Earth and in space and how it affects all of us. And I think if you just consider that in this room, the only things that are not made by the hand of people are the individuals in this room and maybe the water in your cups and in the decanters. What I would want to do is get you thinking of materials science, and maybe that's a tough thing for people who aren't material scientists, but we are all material scientists in a way. And what I'm going to do is I'm going to give you a really brief lecture/story about a material science experiment that occurred a few years ago. Back in '74, it was published, but by a very famous chemist who you will all know. And it illustrates kind of the exploration side to science in general, and then I'm going to have my esteemed guests come up and they're going to talk about material science and space. And I'm hoping that you'll be able to better identify with what they're doing and what they're talking about. Okay, so the first slide. Let's get that. So here's the molecule I'm going to discuss with you. It's actually a very simple molecule, although it looks big and scary. It's the active agent in olive oil. This is what gives olive oil its color, its flavor, its smell and texture. It's actually 3 long molecules, you can see, all attached to a small little molecule at the bottom. And when you buy olive oil, it comes looking like this, but there's also pieces where the big long pieces have come off. Those are the 2 main components in olive oil. This was used in an experiment by Benjamin Franklin. He's the chemist. He ran this experiment back in between 1770 and 1773. It was submitted to the Royal Society Philosophical Section in Great Britain and was published in 1774. And at the time, he was trying to solve a problem, which was that the water in Boston Harbor was often very difficult to navigate, and it was causing problems with shipping. And he had noticed an effect that if you added oil to the water, it actually smoothed out the waves. The experiment that he ran was at a pond outside of London. He was actually in Great Britain at the time when he was doing this. It was some tax negotiation thing he was involved in. And this is the pond where he did it. It's called Clapham Pond. And you can see the effect. The upper slide is before the oil is added, and the lower part of the slide shows the effect that you get when you add, in this case, just a few drops of olive oil to the pond. It may not seem like much, but if you consider that the layer, the film that is on that surface is 1 molecule thick, and yet it has that effect, it is an amazing amount of force that it is able to exert on the surface of the water with something that small, that thin. Here is the actual experimental. This is where he describes what he did 240 years ago. And I was told that I should read it, that some people in the back may not be able to read it. So I'm going to read it to you because I think it's important to do 2 things. One, to describe him as a scientist and the excitement that he had in actually executing an experiment. But it says also something about just him as a person. And you can follow along on the left. That's the untranslated form. It turns out the English language has changed a bit in 240 years. At length, being at Clapham, where there is on the common a large pond, which I observed to be one day very rough with the wind, I fetched out a cruet of oil and dropped a little of it in the water. I saw it spread itself with surprising swiftness upon the surface, but the effect of smoothing the waves was not produced. For I had applied it first on the leeward side of the pond where the waves were large, and the wind drove my oil back upon to the shore. So his first experiment failed. And that happens, right? In this case, it's because it was windy and he was standing on the wrong side of the pond. So you can imagine Benjamin Franklin in his knickers and his shoes that were actually cobbled together by a cobbler running around the pond to the other side. And he continues. I then went to the windward side where they, the waves, began to form. And there the oil, though not more than a teaspoonful, produced an instant calm over the space of several yards square, which spread amazingly and extended itself gradually till it reached the lee side, making all that quarter of the pond, perhaps half an acre, as smooth as a looking glass. So he's run his experiment, and he's seen the effect. Now, the calculation I'm about to show you, he did not run, and I'm going to explain to you why I believe he did not do it. All I did was I took half an acre, which is what he said it spread to. I converted that to yards, and then yards to square meters, so 2,219.9 square meters. 1 teaspoonful, I don't know how big his teaspoon was, but teaspoons today are 5 milliliters. So I went with that. 5 milliliters converted it to centimeters to then 5.0 times 10 to the minus 6 meters cubed. You then divide meters cubed by the meters squared, and you get meters. That is the height of the film. What he did, if he had done this calculation, he was very close, he would have measured a molecule. This is an amazing event if you consider that the whole concept of atoms being stacked up to make a molecule would not be invented. That concept would not be invented for 100 years. He came up with this number, 2.25 nanometers. What does that mean? Well, just so that you know, if you take the Earth and you compare it to the size of a baseball, that is relatively speaking about the same as a baseball compared to a nanometer. To him, that would have meant nothing. To us, it really is very hard to understand. But to him, if he had done the calculation, which he probably did, and just said, what is that? It didn't have meaning. But to us, it does. If you do a comparison between what he would have gotten in his calculation, 2.25 nanometers, and the current calculation for what that molecule's length actually is, look how close that is. That is just remarkable. Looking at the film, we're now down looking at the molecular level. What's happened? Well, I told you that that molecule breaks up and forms these long strands, and that's what they look like. They are these long strands where one end is polar. It's hydrophilic. It likes the water. And the other end, the fatty chain, is hydrophobic. It doesn't like the water. So the hydrophobic part stands up. It tends to group together, and the lower part, the acid, clings to the water, and it holds itself upright like that, and then you get this film. And it is called a self-assembling monolayer, and we use these today. If you've ever used, it's called Windshield RX, you spray it on your windshield, wipe it down, and then the water beads off, you've created a self-assembled monolayer on your windshield. This is used for a lot of different systems, and in fact, your cells, the cell membranes in your body, are self-assembled bilayers. They are 2 of these standing up where the water on either side of the cell membrane is holding them in place. Experiments are submitted to us, and they use some of the same properties. They're using the same things that maybe Benjamin Franklin didn't quite understand, but the same properties are being used. And this is just one example. This is a proposal that was submitted to us from Indiana University and Purdue University, in which they run reactions in drops. They run reactions in drops about the size of a BB. And what they found was the reaction at this surface is going about 1 million times faster than the reaction in the bulk, in the middle of the drop. What's probably happening is the interaction between the outer surface of the drop and the atmosphere is causing all the molecules to line up, and it's acting as a catalyst. They're being lined up, and then they're much more able to react with one another than if they're just sort of jumbled together in the bulk. So we see these types of things, and of course, doing work on space station, you can take microgravity, and that allows you to suspend a drop in midair, where on Earth, that's a much more difficult thing to try to attempt. So what can we learn from Benjamin Franklin? First of all, of course, Benjamin Franklin was a very smart person, right? He was a physicist, a chemist, a philosopher, a founding father, We can go on down the list of what this guy did. He was an elite athlete. He was the real-life Tony Stark of his era. But he's 240 years. What has happened in 240 years? Think about the technology, our ability to communicate. The fact that when he went to find a unique environment to run his experiment, he went to a pond. And we're talking about going to the International Space Station. We have advantages that he did not have, and we can use all the development, the things that we have learned up to this point to design new science that can be done in space. And ultimately, the science done in space will have impact not only on our ability to explore, but on us back here on the Earth. So keep your eyes open. Think about the materials that are all around you. And if you have opportunities that you want to bring to us to run on station, we're always ready and willing to accept those. So I'm now going to introduce the panel speakers. And you guys can all come up. No. If you do have questions, I think the way they're doing it is submitting them through the online tool, the app, and then we'll get them from there. Our first speaker is Corky Clinton, and he's coming to us from the NASA Marshall Space Flight Center. Corky.
Okay. Got the clicker.
Today is Doug Comstock.
Okay, good morning. I want to talk to you about materials and manufacturing as we proceed from space station all the way to the lunar surface. I'm going to start by talking about the materials and manufacturing that we're investigating right now on the International Space Station, particularly for in-space manufacturing. Then we're going to move on to manufacturing, to a couple of projects that were recently announced by STMD for the free volume of space, actually manufacturing and assembling. And then finally, we're going to head to the moon and talk about a new project also that's just come out of STMD that focuses heavily on the use of lunar resources. So at this point in time, I normally talk about why we're doing in-space manufacturing. But for those of you that were here late yesterday afternoon, hopefully you heard Katie Boggs and Chris Moore make that case for me, and I really appreciate them making that case. And I really particularly appreciate Chris saying, you know, this is in-space manufacturing is a critical technology for logistics reduction. And that's the story right there. The space station logistics model is just not going to work for deep space exploration. You don't have a quick abort capability, you don't have fix and fly capability, and you don't have a resupply capability. So to address some of these challenges, we're developing in-space manufacturing technologies. We started in 2014 with Made in Space. You can see the first bullet there at the 12 o'clock position is Butch Bilmore holding his ratchet, which was actually the first part uplink from space, or uplink from the Earth and printed on the space station. Then Made in Space went on, took the lessons learned from that first printer and developed the Additive Manufacturing Facility, or AMF, which is on station now. That is a commercial printer, by the way. They own it, and we buy services from them. Recycling is also a very key technology in being able to recognize logistics reduction. So Tethers Unlimited has flown now the refabricator. It's on space station. Its purpose is to recycle Ultim 9085 and do that continuously. Then Tethers recognized that, hey, if we add a sterilizer to the refabricator technology, we could actually have a food and medical grade sterilizer. Now that's also important because a significant fraction of the waste stream on space station comes from food and medical waste. Then common use materials. We challenged industry to take a look at the packaging materials on space station because the packaging materials are also another source of waste and trash on space station. Please see if you can find ways to turn these packaging materials into feedstock so that we can print parts and components and so forth. Tethers was one of those, and they took a novel approach. They said, okay, why don't we start with feedstock and create a packaging material, and then we can convert that back into feedstock. And the material that they created is actually quite novel, and you can tailor the strength and stiffness for your particular launch load needs. Cornerstone took another approach. You can see the pink anastatic film. They worked that with a reversible thermopolymer, and they can then modify the viscosity so that we can print with it using an FDM printer. Now moving on to about the 8 o'clock position, we're talking about metals work that we're doing to be able to print metals in space. There's 4 technologies that we're funding: wire arc through Made in Space, ultrasonic technology through Ultratech, Tethers is leveraging their refabricator experience, using CMC to machine the billet using an ingot approach. And then finally, we've got TechShot with their simple technology, which is using inductive heating to heat the thin wire and then laser to do the centering of the softened wire. Another bit of experience that we've learned from space station and looking at the problem reports is that a number of the failures that take place are with electronic components. So wouldn't it be great if you're on your deep space mission to have the capability to print whatever you need in the electronics world to replace what's failed? We're working some of that in-house at Marshall. We're partnering with other centers and industry. We're looking at flexible electric circuits, wearable sensors, gas sensors, pressure, temperature, humidity sensors, all kinds of conductive inks, Inconel 718, silver, aluminum tin, and so forth. And then finally, really is the crown jewel that Chris Moore talked about a little bit yesterday. That's the multi-material fab lab. We're in the first phase of a three-phase process to be able to print not only with the same machine plastics and metals. And we gave industry a choice of titanium 6.4 or aluminum 7075. Larger build volume, a lot of autonomy, inline quality control and inspection. So we're asking a lot out of industry. The next phase should begin competition no earlier than very late this year or early next year. Okay, now let's move outside the pressurized volume of space station. Nope, not just yet. This is a quick shot of AMF on orbit. On the lower left, we've got some examples of functional parts that were actually printed on space station and in use on space station. The feed horn was a demonstration project, and we brought that back down to Earth. And then you can see floating in front of AMF is what's called a multi-purpose tool. That was a student winner of the Future Engineers Challenge, and his prize was to see his part get printed on space station. So there it is. And then real quickly on the lower right, we're characterizing the ABS material that comes out of AMF. That's in progress now. We'll follow that up with 9085. Now let's move outside space and go into the free space. Just a couple of weeks ago, you all may have seen coming out of Space Technology Mission Directorate an announcement from their IRMA program. Now, IRMA is In-Space Robotic Manufacturing and Assembly. It was a ground-based program for the last 2 years, risk reduction to be able to move toward a flight demonstration. 2 of these projects were selected to go forward. One is Dragonfly, and it's being worked on by Maxar and Tethers. And Rob may say a few more words about that, as well as some of the other Tethers things that I've talked about. That's primarily focusing on assembly in space, and we expect that to fly with Restore-L. This one is Archinaut by Made in Space. They're taking advantage of technology they developed on the ground to be able to print beams in space. And along the way, they set the Guinness Book of World Records for the longest single printed structure of over 37 meters. You can see Andrew Rush. Mary Beth mentioned Andrew. Now you can put a face with a name. Over there holding the solar array. And the way this works is they will print the beam. They've got a flexible solar array that rolls out as they print the beam. And then they will have 2 of those solar arrays on each side of the spacecraft, giving the spacecraft greater than 2 kilowatts power. You can see the spacecraft there in the center, and it will host a Northrop Grumman payload. There we go. Now let's move on to the moon. This was another newly formulated program out of the Space Technology Mission Directorate, and it's called the Lunar Surface Innovation Initiative, LSII. Now, as we go through this progression of development to return American astronauts to the moon by 2024 and have a sustainable presence by 2028, the Lunar Surface Innovation Initiative is going to focus on those capabilities that are shown in the yellow boxes. So we've got sustainable power. You may have heard Chris Moore say yesterday that will be fission-based power. Dust mitigation, ISRU, surface extraction and construction. And then finally, the access to extreme environments and extreme locations. We have to make sure that we can go explore the moon, and we have to make sure we can survive in the harsh conditions of the lunar night and the lunar day. Okay, you can see this is heavily focused on lunar resources, and in particular the use of regolith. So let's talk about what we're going to do to develop regolith and lunar resources. The first robotic mission to the lunar surface is planned to be a mission to the South Pole. There we're going to extract polar ice and characterize the water that comes from the polar ice. And developments are already in place to move forward toward that experiment. One example is the drill selection, down selection, for honeybee robotics. They're developing the drills for us. And another area that we need to focus on for Earth-based risk reduction and development is utilization of ISRU, the regolith. And a comment was made in the workshop earlier this week that there is no real source of regolith. We're going to need a lot of high quality and common use regolith so that the results we get for the community can be pooled and we understand. We don't have people working with different sources of regolith and we can't understand the results when we put them together. So LSI is taking on that challenge to provide the community with high fidelity simulants for the research and development. One of those uses will obviously be the extraction of oxygen that we can use as a consumable, but also in that extraction of the oxygen, there should be a byproduct of metals. And we want to use those metals as feedstock for manufacturing of tools and components that we'll need, much like we're doing in-space manufacturing on the moon now. We'll transfer those technologies forward to the moon. And then in looking at what is probably the second robotic experiment, that will be processing the regolith on the surface of the moon to see if we can indeed show it as a demonstration of technology, extract the oxygen, extract the building materials. And then as we move forward into sustainability, we will have to scale up those processes to produce consumables, oxygen, water, hydrogen for fuel. And also that's when we'll start to get into the idea of excavation and construction. Well, we could construct there depending on the technologies we use, and there are several out there, laser centering and additive construction, which we're already working on with Earth-based systems. Landing pads, roads, berms, shelters, even habitats, or you can use the technology to pile regolith on top of an inflatable habitat for radiation protection, micrometeoroid protection. So there are a lot of uses and a lot of work that we need to be doing on the lunar resources to learn how to live off the land when we go forward. A lot of work ahead of us, very exciting time. That's what I have for you.
Thanks, Koki.
Yeah.
Our next speaker is Rob Hoyt. He's the CEO of Tethers Unlimited.
So at Tethers Unlimited, our objective is to help create a robust and sustainable in-space economy. And one of the challenges there is that while there are a number of potential markets that a number of different commercial entities are working to develop, each of those markets, whether it's in-space resources, propellant depots, space tourism, each of those markets by itself does not create a sustainable economy. What we see is the capabilities for off-world manufacturing and services can be the linchpin that can help tie these multiple markets together to help bootstrap a functioning economy in space. But one of the other challenges there is that you can't just build one part of that economy on its own. You need to bring up both the supply side and the demand side in unison together to get them operating together to make a functioning economy. So fortunately, NASA has a small business innovation research program that funds innovative new technologies, and we've been making good use of that, trying to address the full spectrum of the off-world manufacturing and construction supply chain, addressing matters such as how do we get materials, how do we source materials in space, and how do we progress from launching materials here on Earth towards being able to utilize materials that we can get in space. Then how do we take those materials and transform them into things of value in space? How do we integrate those things of value into functioning space systems? And then how do we take those unique objects that we can create in space to provide new services to customers in space and here on Earth? So I'd like to tell you about a few of the SBIR-funded projects that we've been working on and how they relate in particular to materials science and work we're doing on the space station. The first one is the Refabricator project. That's a roughly mini fridge-sized payload that combines a plastic recycling system with a 3D printer, and it's intended to demonstrate closed-cycle recycling and manufacturing capabilities to support long-duration manned missions. So an astronaut can put in pieces of plastic waste, they get melted down and turned into 3D printer filaments, and then the machine can print new items that astronauts could use. We're also working on a couple of related projects. The CRISP project has been developing launch packaging materials that can replace the disposable foam and bubble wrap and Ziploc bags that are currently used to protect items going up to the space station and then become trash that the astronauts have to stuff in a corner somewhere. We're going to replace that with new packaging materials that are specifically designed to be recycled into high-quality 3D printer filament. And then we're also working on the Erasmus SBIR project, where we're integrating 3D printing and sterilization capabilities so we can make food-grade and medical items to support long-duration manned missions, so that on a mission to Mars, you don't have to carry dozens and dozens of urinal funnels for the space toilet. You can carry just a few, we can clean them, sterilize them, and reprocess them, and greatly reduce the amount of mass that needs to be launched to support long-duration manned missions. And one of the reasons I find this project really exciting is that we're using the challenge of supporting logistics on the space station to help drive us towards a capability that eventually here on Earth could provide capabilities for localized recycling and localized manufacturing. So that instead of generating megatons of carbon, shipping our plastic waste over to Asia, and then more megatons of carbon shipping plastic items back here to the States, we can enable communities and businesses to recycle and remanufacture materials locally so they can handle their waste in a more economical and environmentally conscious manner and more rapidly create the new items that they need. Another project we're called Mantis. We're developing and integrating a compact robotic arm that's designed to be safe to operate around astronauts into a payload to enable remote operation of experiments on the space station. And how does that relate to material science? Well, material science often involves doing the same operation many, many times so that you can get good statistics on the materials processes. And that can get boring. So what we want to do is to offload those menial and repetitive operations from the expensive and very busy astronauts to underpaid grad students on the ground. And so that's another capability that we're working towards. And then the last project I'd like to talk about is a public-private partnership between NASA's In-Space Manufacturing Program and 3 small businesses, and we're very fortunate to be one of them, to create what's called the Fab Lab. And the objective there is to create capability for precision manufacturing of mission-critical parts. And that system will integrate metal 3D printers, hopefully metal milling systems, inline inspection capabilities, and robotics, so that we can have a fully remote capability for manufacturing metallic parts that astronauts need to maintain their space systems and do their missions. And one of the interesting challenges that project is getting us into is that in making metal parts, it's not just a matter of milling a piece of metal. Making metallic parts often involves heat treatment and quenching processes to get the right metallic characteristics. And on the ground, you often do the quenching by dropping the piece into a vat of oil or other fluid. But how do you do that in zero-G? And how do you do that in a way that's going to be compatible with space station safety requirements? So that's another project that's helping to push forward some of the material science investigations that we're doing at Tethers Unlimited. Thanks.
Thanks, Rob. Our next speaker is Teo Liano, and he's coming to us from IBM Research in Zurich.
Thank you, Ken. Good morning, everyone. In the next couple of minutes, I would like to give you just a very brief overview on how the paradigm of material discovery is changing in these years. So for doing that, I'm going to talk about materials, I'm going to talk about knowledge, and about artificial intelligence. First of all, how are we discovering materials today? How did we do in the past decades? We always, if we analyze carefully, whether it's in the pharma industries, whether the example of Franklin was a very nice example, we always started from an opportunistic discovery. We started from something that was either crossbreeded from other fields and then brought into a completely different context to solve a specific problem. That's a sort of development which is a diverging development. So we started from an initial idea, and we have been constructing and generating a lots of data, a lots of knowledge, starting from that initial seed. Eventually, out of this entire exploration, only one among all the possible analyses and all the possible materials will really make it into the market. Now, there is a side effect in this sort of paradigm for materials discovery. And the side effect is that we are generating lots of data that in the best of the cases is sitting somewhere in some servers, in some storages, internal in companies, or whether they are governmental offices. And it's always a continual rediscovering of ideas. Now, we envisage that, and we are not the only one in IBM research. It's a very interesting moment because there is a very clear understanding of what artificial intelligence can do also to solve the problem of designing materials. But we believe that we can construct and leverage the knowledge that is accumulated across the individual project leading to a discovery of a material to have a converging type of paradigm. So in the future, and what is happening already today, is that instead of starting actually from an opportunistic discovery, we are starting from analyzing a large extent of data, having in mind the problem that we want to solve, and using the entire data set for fine-tuning the right material for a specific application. Now, at the core of all this paradigm is, of course, AI, artificial intelligence. One of the reasons why artificial intelligence is actually very useful, and again, the example of Franklin is very propedeutical. It's going back to 240 years ago. You can imagine how much literature and materials we have been generating in the last 250 years. Only in this chart, in the chart you can see on the top left, you can see more or less the exponential growth of publications for articles in the context of materials. And only a few years ago, in 2015, we were more than 350,000 articles generated only in that field. It's humanly impossible to explore and analyze all this knowledge. We need to rely on different type of solutions, and in this case, artificial intelligence is the most successful one, to process this information, going through the entire set of documents. So we need to understand the dark data that may be generated on Earth, it may be generated also on the ISS, and we need to combine the knowledge that is extracted from existing documentation with the knowledge that we will be producing also in the future. And in this context, actually, space exploration, that the ISS is going to be a tremendous laboratory, because some of the knowledge that we can extract and analyze on Earth is actually generated in conditions that are completely different from the conditions that are available in the outer space. And they're basically, that type of knowledge is strongly complementing for the material discovery process the knowledge that we have collected on Earth. The other thing that you want to do, and this goes in the direction of combining also consumable production eventually on future missions on Moon or on Mars, is that you need to have this knowledge readily available. You need to have the entire 200, 300 years of materials knowledge readily available for whoever is going into the mission. So in this context, it's very, very difficult to believe that whoever is going this mission is going to have an exhaustive knowledge, whether it's in this domain of aluminum alloys or in the domain of polymers. So it's important that the work of analyzing knowledge, constructing what is called today knowledge graphs. So they are graph of knowledge where the entities are semantically connected with each other, is readily available for anybody that may need that, either for the processing or, for instance, for automatizing some of the experiments. And this goes in the direction of the Fab Lab that we have seen before. Materials discovery goes through a series of automatic tasks, that's correct. And in this context, having a sort of brain with the entire knowledge accumulated in the humankind area is actually an incredible, powerful tool to lead to the entire automatization. So I want to close it here, and I think we can go on if there are questions. Okay.
So we're going to go through some questions just amongst us, and then if any come in, I'll feed those to you as well. So based on what we've just seen, what are the next steps we need to be thinking about? Like, what are the things we should be doing beyond what's going on right now? Sort of we'll say, an intermediate plan forward. Starting with you, Corky. And I'm thinking about materials, like where we're headed with materials, whether it's to understand how we're going to get ourselves to the moon or Mars, or to think about what we can learn that can be applied back on Earth.
Well, the one thing that I'm encouraged about, particularly in some discussions with Fran and Craig Coonrod, is the increasing synergy between what they're doing on space station with material science, what we're doing on space station with more of a materials engineering type of an area, and seeing a convergence of those with common objectives. And we can certainly use the information that the material scientists will develop to help us make better products on space station. So I do see that going forward, and utilizing their scientific background to help us. The other thing that I see going forward, there's an awful lot of work that needs to be done on regolith and in situ resources. That is key. I forget who said it yesterday, probably multiple speakers, but if we're going to go and have a sustainable presence on the moon, we have to be able to learn how to live off the land. And what we have there to live off is the regolith. I'm putting aside other resources being the water ice for oxygen and hydrogen and water. But what can we get out of the regolith? What can we do with it? That is a material science problem. That is a regolith chemistry problem. That is a processing problem of materials at its best scale. So that's an area where I think we can really benefit from the material science aspects, feeding that back to the risk reduction activities on the Earth so that we can then demonstrate that technology on the moon.
Is that going to require us to bring material back here? Is that what you're talking about?
Well, that would certainly be a help, because then we know exactly what we've got. But based on the Apollo samples, the JSC-1 sample was a notable one that was out there fairly common years ago. I think that was the comment on Monday, that it's not around anymore. We need simulants, and we had a program back about 10 years ago that was carefully constructed to try to mimic the conditions, particularly the constituents and the density and the structure. But that soon died, but that formula is still there. We need that to give out to the researchers based on the Apollo samples. But as soon as we get more samples back, that will certainly help us refine the particular recipe for the areas that we want to land.
Okay. Rob, same question. So what do you think we need to be doing right now, as in sort of thinking about for intermediate term to get us to where we need to, whether it is exploring or just understanding new materials or production back here on Earth?
What I'm most interested in is that question that I mentioned early in my intro of how do we progress from using materials that we launch from here on Earth to build things in space towards using materials that we can source in space. An example of that is under the Dragonfly program, we're going to be demonstrating capability for manufacturing large composite structures on orbit. Basically, we're going to be making 2x4s in space to enable construction of structures. But we're doing that by launching carbon fiber composite materials from here on Earth, which is still expensive. What we'd like to progress to is using in situ resources to make composite structures and other materials. So one project we'd love to work on is, can we use lunar basaltic materials to make basalt fibers that can replace the carbon fibers in manufacturing composite structures in space? And I think there are a number of other opportunities there. How do we process metallic materials we can get on the asteroids, on the moon, into billets of metal that we can machine or otherwise process to make useful parts? There's a lot of material science needed to be done there to take, the titanium oxide or other, you don't just find, it's rare that you find pure ingots of iron or titanium lying around. You've got to get the lunar regolith and do a lot of processes on it to get useful materials out of it. And there's a lot of questions there of, many of those processes involve a number of nasty chemicals to separate the materials and purify them. How are we going to handle those? How are we going to supply those chemicals? How are we going to handle them? How are we going to recycle them so that we can set up a sustainable infrastructure for transforming in situ resources into useful feedstock for in-space manufacturing?
So I'm going to change the question a little bit for you, Teo, but it's around the same kind of idea. What do we need to do to enable ourselves to better be able to predict or select materials in the future? Is it just a matter of being able to get the right data organized in the right way? Or should we be thinking about how we design the experiments that we run and with a forward-thinking approach to how we're going to use that data? What are your thoughts?
So I would also like to connect to the previous question. It's the manufacturing aspect is actually very important. And if you think to a sustainable manufacturing, you need to also provide the independency to the people that are doing the manufacturing. So in this context, again, having as much as knowledge possible on chemical processes, manufacturing processes, and how to better optimize them is a key point. Then connecting to the last question Kenny said, it's important. Data is somehow the pillar where the new materials discovery, the accelerated material discovery is centralized. So it's important to have as much as possible data that is spanning different type of conditions. And again, I want to stress the fact that on the ISS today, we can do experiments on materials that are complementing, really not only augmenting, but complementing the type of data that we are collecting on Earth today, just because the conditions are completely different. So in this context, it's truly important that if we want to go in the direction of building materials for a specific mission, we have data today, or we are going to make available data that is covering as much as possible the condition where the material will have to be optimized. So it's a key aspect, and of course the entire experimental design that we may go today thinking is important for guaranteeing that any data that we are collecting out of experiments are not just duplicates, but are complementary to what we have.
So in selecting materials, I'm sure there's a process that we go through, and for things that go into orbit, or even for experiments that we're going to run, we think about what the material requirements are. But we often have to make changes based on use or other situation. Do you have any examples? I'll start with you, Rob, of situations where materials have been changed from the original plan to something new based on some requirement or some new application or what have you?
Well, in choosing materials to work with on the refabricator, on the ground, typical 3D printing materials are things like ABS and, well, ABS and materials like that. The challenge for those is that those plastics have relatively high outgassing or off-gassing properties, so they're giving off volatiles all the time, and that's a challenge in a contained environment like the space station. So for the refabricator, we started out working with materials such as Ultem and PEEK, which are very high temperature thermoplastics that are challenging to work with, but they're good for space applications because they don't give off those volatiles. So you need to factor in environmental characteristics, like what gases they might give off. Additionally, in processing them on the space station, what we found is one of the challenges is the space station atmosphere is very humid, and that can affect the plastics because the plastics absorb it and it changes their melting temperature and their other properties. So we may need to, you need to factor that in and ideally work with materials that minimize those challenges.
So, Corky, I have a question for you about creating a sustainable presence on the moon. And it's around, what do we need to think about when we consider that, beyond reuse of regolith for multiple purposes? Do we have to consider, and I don't want to come across as being kind of a green person, but environmental issues on the moon? Does that even apply?
That's an interesting question. I heard one of those similar questions discussed in a workshop about planetary protection. Certainly not my area of expertise, but I'll throw out an answer for you. First mission is going to be assessing and characterizing the water from polar ice. We got to be very, very careful that in doing that, we don't contaminate the water or add some contaminants or other constituents. Has to be a pristine sample, has to be analyzed so we know if there are contaminants. And there have been discussions about fluorine and other things present in the polar ice that we may not want to have to deal with or have to filter them out. Other than that, we're going to be rearranging the surface of the moon. We're going to be spreading dust everywhere when we land. We're going to be mining. We're going to be extracting materials. We're going to be building materials. But I would say one of the things that should be beneficial out of that is we're going to use the local materials. The idea is to bring as few materials from Earth as we can. I mean, we don't want to launch Portland cement to the moon. We want to use what's there. So that should be about as green as we're able to get when it comes to the moon.
Okay. So I've got a question for all of you. We'll go through each of you. So we're talking about exploration in space and doing things on the ISS. Can you talk about this and what we're talking about here and its impact on the people on Earth? So, and it may be processes or understanding or information that we bring back and can use. So we'll start with you, Rob. Just talk a little bit about what you're doing and then how it applies back to people on Earth, what they're going to see.
Well, as I mentioned, one of the reasons I'm really excited about the refabricator is we're again using the challenge of addressing logistics problems on the space station, addressing the waste and material supply to help drive us towards a capability that eventually could enable localized recycling in manufacturing. There's still a lot of work to do to progress from the refabricator unit that's designed to operate on the space station towards one that is economical enough to deploy in communities and in businesses. But the work that's been funded under NASA's SBIR program has moved us significantly in that direction.
Okay.
Yes. So, well, the entire paradigm that I was describing is, of course, initially started here on Earth. But I'm a strong believer, as I was mentioning before, that the innovation for materials, especially in this a new way, which is a convergent way, it's very difficult to track down what are the components in terms of knowledge that are really giving a contribution to the discovery of a new material. So in this respect, it's important that the entire pond, knowledge pond, where we are training artificial intelligence model for designing material, is having as much diverse information as possible. And the benefit for the people on Earth of doing experiments in the ISS or in contexts that are outside of the Earth is actually the one really of having unique data points in conditions that are very difficult for us to explore. And how this is then blended to come up with a unique discovery, well, it's of course non-linear. It's absolutely not clear, but there is a very big potential in complementing the data that are generated on the ISS or in future missions on other planets with the data that we have here to create new materials.
Thanks. Gorky?
I'll give you one example that we've been working recently with the Corps of Engineers. It's a dual-use technology for Earth and for construction on extraterrestrial surfaces. And it's exactly that. It's additive construction to create structures that the military will need in forward operating bases. You know, they don't want to have the logistics nightmare. They want to use local resources. They want to reduce the risk to the folks that are building the structures in these forward operating bases. So they want an automated process that will come in, set up their base. We want to do exactly the same thing, but we want to do it on an extraterrestrial surface. We want to use local materials. We want to do it autonomously and not have the crew have to be involved in that. So these two technologies, the off-planet and the on-planet, are progressing hand in hand. We're using what we learn here on Earth. One of the challenges we face going forward is we can print the structures, but we can't yet print a functioning house, which includes the electrical, the reinforcement, the plumbing, the mechanical structures, things like that. And we have to learn how to be able to do that. That would be a wonderful feed forward to the surface of the moon, where we can build a functioning habitat and not just a shell.
Okay, that's great. Thank you. So we're out of time. I'd like to thank our speakers. Join me in thanking our speakers again, Gorky, Teo, Rob. And we didn't get to any of the questions from the audience. If you have any questions, you'll see us wandering around. Feel free to come up and we can talk to you one-on-one.
So thank you to Ken and all the panel members for sharing their observations and visions for a successful materials science research ecosystem on ISS. At this point, we do have a very short break until 11 o'clock, but you should come back and make sure you're on time because we'll have two of the industry leaders in here, Aaron Usman and Steve Lindsay will talk to us from Sierra Nevada. In the meantime, be sure and stop by the Innovation Forum and help your colleagues solve problems or identify yours and see if you can get some help. So we hope to see everybody back here at 11 o'clock. Don't be late. Thanks.